In the fifth lecture on statistical methods in high-energy physics, we will conclude our introductory chapter. In the previous videos, we've defined a pretty general framework for working with probability density functions. We worked out everything in quite a general way, and we didn't assume any specific shapes of the probability density functions. In common practice, people tend to use just a couple of probability density functions most of the time. The most renowned PDF ever, the Gaussian distribution, is often used as an approximation for an unknown probability density function. There is a good reason for that, as you will see later. The Gaussian distribution is so great and it fits so many situations that it got the most fantastic reward. People started to call it normal distribution. Let's listen to what the famous statistician Poisson said. Many years ago, I called the Laplace Gaussian curve the normal curve, which name, while it avoids an international question of priority, has the disadvantage of leading people to believe that all other distributions of frequency are in one sense or another abnormal. The other distributions are of course definitely important, and we will present some of them shortly. Before doing it, let's stress that each probability density function is, of course, a function of a random variable or multiple random variables. At the same time, it often has additional parameters which affect its shape. For example, for the Gaussian distribution, these parameters are mu and sigma, the mean and width of the Gaussian peak. In the frequentist framework, the probability density function parameters are fixed numbers, and we use the notation f of x semicolon theta, or f of vector x semicolon vector theta. In the Bayesian framework, the PDF parameters are random variables, and we use the notation f of x given theta, or f of vector x given vector theta. This notation is the same as for conditional probabilities, and actually this is how we view the PDFs depending on parameters in the Bayesian statistics. Unfortunately, the Bayesian way of denoting probability density functions became so popular so that it is often used even in the frequentist framework despite the risk of confusion. Finally, let's stress that each probability density function must be normalized to unity when integrated over the random variables, but not over its parameters. So it is important to distinguish between random variables and parameters when writing down the symbol for the probability density function. Let's have a look at the most important properties of the most common probability density functions. We must definitely start with the normal distribution. In one dimension, it has two parameters and is denoted as n of x semicolon mu sigma equals to 1 over square root of 2 pi sigma times exponential of minus x minus mu squared over 2 sigma squared. With this definition of the normal distribution, we will heavily profit from the definitions of the mean value and variance. Expectation value of x equals to mu, and variance of x equals to sigma squared. In n dimensions, the normal distribution is defined as follows: n of x vector semicolon mu vector v equals to 1 over 2 pi to the power of n over 2 times determinant of v times exponential of minus x vector minus mu vector transposed times inverse of v times x vector minus mu vector. Here v stands for the covariance matrix. As you probably expect, the mean values of the individual variables are mu vector and the covariance matrix is V. Expectation value of x vector equals to mu vector and covariance of xi xj equals to v sub ij. The extraordinary importance of the normal distribution heavily relies on one fantastic fact, which is being referred to as the central limit theorem. Very roughly speaking, the theorem says that the sum of many random variables is a normally distributed random variable. Let's be more concrete. Suppose that we have a sequence of independently and identically distributed random variables x1, x2, x3, etc. The mean value and variance of the PDF are e of x equal to mu and variance of x equals to sigma squared, which is finite. Let S sub n be an average x1 plus x2 plus xn over n. Then as n goes to infinity, the random variable defined as y equals to square root of n times Sn minus mu converges in distribution to the normal distribution with mean at 0 and width equal to sigma. Under certain circumstances, the theorem is valid even for variables that are not independent and or not distributed according to the same probability density function. Isn't this wonderful? It means that if you estimate mean value of a probability density function with an average of measured values, then your estimate is normally distributed. In 1837, S.T. Poisson introduced a probability density function that describes distribution of an integer random variable that counted the number of some events that occur during a time interval of a certain length. It was part of his work about the number of wrongful convictions. During the time, this PDF served to model the number of soldiers in the Prussian army killed accidentally by horse kicks, or the number of stars found in a unit area on the sky. Particle and nuclear physics use the Poisson distribution extensively. It describes the number of radioactive decays of a certain isotope in a unit of time, or the number of particle collisions yielding a certain result. The probability for n events to happen is given by a simple formula. F of n with parameter nu equals to nu to the power of n over n factorial times exponential of minus nu. Of course, n is an integer value. The only parameter of the distribution, nu, is a positive real number. For the mean value and variance, we get expectation value of n equals to nu and variance of n equals to nu. Note that the bin content of a histogram is usually distributed according to the Poisson distribution. Let's move to coin flipping now. It can be an adrenaline sport if you bet large amounts of money. However, we will study it from a professional point of view. A coin flip is actually an experiment described by the binomial distribution. One flip of a coin is an experiment with just two outcomes, heads or tails. Let's denote the probability of getting a heads toss as P. If we flip the coin n times, then the probability of getting k heads is given by the binomial distribution f of k with parameters n and p is equal to n factorial over k factorial times n minus k factorial times p to the power of k times 1 minus p to the power of n minus k. Let's stress that generally the probability p doesn't need to be 50% like it would be in the case of the conflict experiment. The mean value and variance of the binomial distribution is given by expectation value of k equals to n times p variance of k equals to n times p times 1 minus p. You will meet the binomial distribution in particle physics when determining an efficiency of a detector. You take n events and you accept k of them. The distribution of the number k is binomial. The last probability density function of a huge importance for particle physics is the chi-square distribution. It has much less poetic meaning than the binomial one, but we will meet it much more often. Let's suppose we have n independent random variables, and each of them is distributed according to the normal distribution, with mean equal to 0 and width equal to 1. Then the variable chi-squared, defined as a sum for I going from 1 to n of xi squared, is distributed according to the chi-squared distribution. Note that the variable and its distribution are both called chi-squared. It can lead to a confusion if you don't know about it, but most often it's clear from the context. The mathematical prescription for the chi-squared distribution is f of chi-squared with the degrees of freedom n equals to 2 to the power of minus n over 2 divided by gamma function of n over 2 times chi-squared to the power of n over 2 minus 1 times exponential of minus chi-squared over 2. It's clear that the only parameter, n, is a positive integer. It's often called a number of degrees of freedom. The mean value and variance are expectation value of chi-squared equals to n, and variance of chi-squared equals to 2n. Note the tight relation of the chi-square distribution to the normal distribution. If x is distributed according to the normal distribution 1 over square root of 2 pi sigma times exponential of minus x minus mu squared over 2 sigma squared, which equals to 1 over square root of 2 pi sigma times exponential of minus 1/2 q, then q is distributed according to the chi-square distribution with 1 degree of freedom. We get a similar relation even for correlated variables. If x is distributed to the normal distribution with the mean value equal to mu vector and the covariance matrix V, then the random variable q, defined as x vector minus mu vector transposed, times inverse to the covariance matrix times x vector minus mu vector is distributed according to the chi-square distribution with the degrees of freedom equal to d, where d is the dimension of the vector x.